All right, welcome to section number 9, designing a layer 2 campus. In this section, we're going to look at some of the design elements of a layer 2 enterprise network and some of the typical technologies that we're going to run inside of that enterprise network to support things like resiliency, being able to recover from issues with maybe a loss of a device or loss of a path. Of course, security is always going to be a major concern, not only in the choice of protocols that we use and how we implement those protocols, and also how we secure the elements of security for the endpoints themselves. We'll take a look at quality of service. Later on in this course, we have a whole module dedicated to quality of service, a couple of different modules dedicated to quality of service. But we're going to talk about VLANs, we're going to talk about trunks, we're going to talk about the VTP protocol, the VLAN trunking protocol. We'll be talking about spanning tree quite a bit. Also understanding multiple spanning tree, power over Ethernet, EnergyWise, and how EnergyWise fits into our environment. We'll also take a look at different port aggregation considerations, first hop redundancy protocols, what are our network requirements for applications. And so most of this stuff is going to be related to layer 2, but we'll take a look at some of the layer 3 resiliency and redundancy options as well in this particular section here. But let's start by talking about some of the considerations that we have for implementing VLANs in our network, as well as trunks and the VTP protocol. Certainly we have quite a bit to talk about with regard to the VTP protocol. We know that the access layer is there to provide connectivity for our end users. And we're going to have different types of devices that have different connectivity requirements at the edge of the network. The edge of the network has changed quite a bit over the years, right? Over time, we went from simply just trying to provide some sort of broadcast domain connectivity in the form of associating an end user's host port to a VLAN to implementing full-on services at the host edge for things like 802.1x extensible authentication, where we can use things like network access control elements to provide device posturing and profiling, providing power over Ethernet for a wide class and range of devices. We'll talk about the different power over Ethernet standards that we have today. In the past, it was maybe a class 5 device or a class 1 device, and we've vastly increased the number of devices and the amount of power that we can provide for those devices, and even incorporated the use of power-saving techniques like EnergyWise elements to reduce power consumption when devices are not being used or utilized in the network, to providing full-on converged access services at the edge, integrated voice, video, and data, which requires the separation of that traffic into different broadcast domains, application of different security parameters to those types of traffic, and then also the ability to facilitate in that network QoS and other requirements that different types of devices require. We also incorporate the use of dynamic security elements, downloadable ACLs that can be applied to a port, dynamic VLAN assignments, device profiling and device remediation, all kinds of things that we're doing at the edge of the network. So we have to take into account a lot more than we used to when we were simply just saying, you know what, port A is in VLAN 10, port B is in VLAN 20, and we're going to have different VLANs that service different types of functionality. Some trunk considerations as well. When we consider implementing trunks, one of the things that we decide to identify is whether or not we're going to implement some sort of dynamic trunking process. There is a protocol called DTP, the Dynamic Trunking Protocol. And the dynamic trunking protocol provides us the ability to essentially automatically negotiate the trunk status of a port. Just a quick refresher on trunk interfaces. Trunk interfaces are interfaces that are not specifically assigned to a particular VLAN, but they do pass traffic for multiple VLANs. Anytime an interface needs to pass traffic for multiple VLANs, it would be implemented as a trunk. But when we do implement trunk interfaces in our enterprise, we consider some of the security requirements that a trunk might have. Are we going to allow all VLANs across the trunk? Are we only going to allow a subset of VLANs across the trunk? Are we going to implement manual pruning of those VLANs? Or are we going to implement some sort of dynamic pruning mechanism using VTP pruning techniques? In addition, do we want to allow dynamic trunk negotiation? Most Cisco switches come with some form of DTP enabled on the device. Let me pull up my pen here. Some sort of function on the device that allows for the negotiation of trunking. Whether it is a function that like dynamic auto, which is a passive function that says, you know what, I will become a trunk if I see DTP messages that indicate I should become a trunk, but I will not actively try to form a trunk link with the device on the other side. Auto is a passive trunking control protocol. Or am I going to run desirable? And desirable is where the interface will actually make an attempt to negotiate the interface as a trunk by sending out DTP messages. And if the other end of the link accepts those DTP messages, we can negotiate the interface to be a trunk. Now, traditionally, in our environment, the switches that would operate in auto mode would be your typical access layer switches, switches that would be at the edge of your network, maybe a lower class of switch, if you will, that maybe a little bit more, a little bit less robust, maybe a little bit less expensive. And then your data center type switches would be the switches that would be operating in dynamic desirable mode. So when you plugged a data center class switch into an access class switch, access layer class switch, we'll call it distribution layer class switch to an access layer class switch, the trunk would get negotiated automatically. All right. Now, the concern in this particular case is that we're running a protocol that automatically communicates the need to create a trunk. And anything that is auto means you probably auto not use it because it is going to be susceptible to some form of attack. And so in most cases, we like to statically assign our ports. We like to statically configure our ports either as a trunk or as an access port, and we don't allow that negotiation. There's a very common type of layer 2 attack in most enterprise networks called a VLAN hopping attack. Think about it. If I'm running DTP on an interface and a host is plugged into that interface, all they would have to do is load up an application. There is an application actually that you can download called Yersinia, Yersinia. It is a Linux-based tool that allows you to generate various types of layer 2 and some layer 3 LAN connectivity protocols. And one of those protocols is DTP. So if I can launch that application on the client and start generating DTP messages, then that port is going to become a trunk. And now I can start tagging frames using 802.1q, and I can start launching either denial of service attacks or some sort of access attack or man-in-the-middle attack, whatever it might be, on various VLANs because I've now negotiated a trunk interface. And Cisco interfaces by default, when they become a trunk, unless pruning has already been previously configured, will allow for every VLAN across that trunk that exists in the local VLAN database. on the switch. So DTP, we had good intentions with this protocol to allow us to automatically negotiate a trunk link, but at the same time, it also opens up a lot of susceptibility. Now, we do have two different trunking protocol options, 802.1q, which is an IEEE standard for trunking, and interswitch link. They define it as obsolete in the book, but believe it or not, it still exists in a lot of Cisco iOS platforms. ISL was developed by Cisco. Cisco kind of came up with the idea of creating VLANs and trunks to segment broadcast domains and separate traffic. But the problem with ISL, and pretty much the reason why it became obsolete, is that it added a significant amount of overhead. If I'm not mistaken, I think it's 22 bytes of overhead for a 14-byte Ethernet header. So, 18 bytes if you count the frame check sequence, but, well, we would always have that frame check sequence anyway. So you're talking about increasing more than doubling the size of an Ethernet frame just so that you can identify the VLAN that a particular port might belong to. So 802.1q has kind of become the standard tagging method. The point of 802.1q is not necessarily to identify what VLAN the host traffic belongs to at the edge where the ingress and egress traffic goes in and out of the switch to the host, but more importantly to identify what VLAN the traffic belongs to as I go from switch to switch. And that's a very important concept. But going back to DTP, dynamic auto, dynamic desirable would be one of the most likely the default options, which means that the port is negotiating whether or not it can become a trunk, either passively or actively. That's why you see if we have a dynamic auto port connected to a dynamic auto port, oops, sorry about that. Let's do that again. A dynamic auto port connected to a dynamic auto port, the port negotiates to be an access port because you have two ends of the trunk that are passively waiting to be told to become a trunk. And, it's kind of like two shy kids on a date. If one person doesn't make the move, then the fireworks don't happen, right? So in this case, dynamic auto to dynamic auto, the trunk's not going to get negotiated. If I go desirable to auto, then the trunk will get negotiated because this side is saying, hey, I want to become a trunk. And the other side is saying, okay, you want to become a trunk, we'll go ahead and become a trunk. Now, the reason why trunk to dynamic auto works is because when you set up a trunk interface by going into the interface and typing the command switch port mode trunk, it actually does still send out DTP messages. So when you do trunk to dynamic auto, we will negotiate to be a trunk because trunk interfaces still generate DTP messages. If you execute the command switch port no negotiate on the trunk interface, that trunk interface will no longer generate DTP messages. And in this case, the trunk would not form if one side is set to trunk with no negotiate and the other side is set to dynamic auto. So it's something to keep in mind. The reason these two are highlighted is because they're saying, you know what, let's go ahead and do our static configuration on both sides of the trunk. We'll go ahead and say switch port mode trunk. We'll also probably use the switch port no negotiate command. It's not a big security concern because the interface is already a trunk. So we're not concerned about somebody forcing an interface to become a trunk. But there's really no reason to run DTP if we've already hard-coded both sides to become a trunk. And if I go into my interface and I say switch port mode access, switch port mode access hard sets the port to an access port. You guys have probably seen that command in your various dealings with Cisco configurations and so on. A lot of people think that, some people perhaps, think that having the switch port mode access command is required to configure a host port. and it's actually not required. We have to set the VLAN that the port is going to belong to, but we don't necessarily have to statically set that port to an access port by saying switch port mode access. All right. By entering the command switch port mode access, we're disabling the dynamic trunking protocol. So if a host connects to that port and starts to generate DTP messages, it's all going to be for naught because the port is no longer running DTP. All right. So dynamic auto says basically I'm going to go ahead and create the trunk if I'm told to become a trunk. Dynamic desirable means I'm going to actively pursue trunk status on the port by trying to communicate that I want to become a trunk by sending these dynamic trunking protocol messages. Trunk is kind of unconditionally setting the port to become a trunk, but it still does send DTP messages. And again, using the switch port no negotiate command would be necessary in order for us to disable those DTP messages from running across the trunk. Switch port mode access, the trunking is not going to be allowed. We're essentially hard coding the port to an access port, and switch port mode access does disable DTP. So even if I do receive DTP messages on a port with the switch port mode access command, the port is not going to negotiate to become a trunk. And certainly when we're configuring a trunk, there are some other things to consider from a general design perspective, right? By default, trunk interfaces allow all VLANs. Now, when I say all VLANs, I mean all VLANs that exist in the local database. So if a VLAN doesn't exist in the local database, it is not going to be added to the trunk because there's no spanning tree instance for that VLAN, and so the VLAN is essentially non-operational. So one of the considerations from a security perspective is you may decide to prune VLANs off of a trunk. We would use the switch port trunk allowed VLAN command to do that. And we would specify what VLANs would be allowed across the trunk. In addition, there is a native VLAN. That native VLAN is VLAN 1 by default. Essentially the native VLAN is a VLAN that is not tagged. There was a reason why we had this in the past. A lot of people are not necessarily aware of why we have the native VLAN, what it would be used for, but in the past you may have had a switch and to extend the length of that segment, because we were limited to 100 meters, you might put some sort of hub or repeater in between and then maybe have another switch at the other end of that link. So this is a layer 2 device, this is a layer 1 device, this is a layer 2 device. And what would happen is as traffic came in, let's say it's coming in on VLAN 10, right? The tagging occurs at the egress port here. And keep in mind that the purpose of the tag is not necessarily to separate the traffic. The traffic is already kind of logically separated based on the fact that it does exist at a different VLAN, and switches by default are told that you're not allowed to duplicate traffic from one VLAN to another. The only way to do that would be to go through a layer 3 device or a router. But the MAC address table in this switch, the CAM table in this switch, is uniquely separate from the CAM table in this switch. And the CAM table is how we identify what VLAN traffic belongs to. So this port is assigned to VLAN 10. When a frame comes into that port, we identify host A as being on port 1 in VLAN 10. So we know that, as an example, if I want to flood this frame, I'm only allowed to flood this frame out of interfaces that are participating in VLAN 10. which would include the trunk link, because let's just say we allowed VLAN 10 across the trunk. The reason why the .1q tag is applied is because when that traffic arrives at the other side, this switch needs to know what VLAN it's allowed to forward the traffic into. And because it sees a tag of VLAN 10, it knows that it's only allowed to flood or forward that traffic out of interfaces in VLAN 10. So the tag actually gets imposed on the egress side of the trunk, and then the tag gets deposed on the ingress side of the other trunk, not at the edge of the network, not at the host port. The host port is a member of a VLAN, but the tagging is only occurring on the trunk link itself. But what if I did have a device in the middle? And this is obviously not something we would do today, but maybe I do have a PC that's hanging off of here, and it happens to be in the same subnet as the other devices in VLAN 10. The problem with that is this tag traffic, so we've got this tag that gets applied to the VLAN 10 traffic. If that goes over to the hub and that information gets duplicated to that port, which it would, that's what a hub does, the PC is not going to know how to process that information because it has 4 bytes of additional information included in the tag. The tag itself is 4 bytes, and it changes the entire format of the frame. PCs aren't generally programmed to understand, host PCs aren't generally programmed to understand how a .1q tag works. So the problem is that PC now drops that frame because it doesn't look like a normal frame. So we have this concept of native VLAN, where I can specify the native VLAN on the trunk interface, and whenever traffic goes into that native VLAN, that traffic is not tagged. And the point of that is that we would want to be able to allow that untagged traffic to be able to go to that device in between, and then also to go to the other side of the link. Because the native VLAN is configured to be the same on both sides of the link, when that receiving switch gets that traffic and sees that it's untagged, it's going to say, oh, this is untagged traffic, so it must belong to VLAN 10 because that's the native VLAN that was configured on the interface. And so we'll associate that traffic to VLAN 10 because that was the native VLAN that was configured on the interface. So why am I giving you this history lesson? Well, the primary reason is because a lot of people have questions in the design function as to how the native VLAN should be used. And there are various arguments on how the native VLAN should be used. In my opinion, the native VLAN should not be used at all. And you can actually go into a Cisco switch and you can say .1q tag native. That's a global command. And you can force all traffic to be tagged, including the native VLAN traffic. There's really no reason not to tag all traffic going across the trunk. Now, a lot of people are maybe not aware that that particular command exists. It's not taught a lot in a lot of the documentation, a lot of the classes. So instead, what they say is, you know what, you should go ahead and use the native VLAN for as a VLAN that doesn't carry any traffic. So in other words, let's go ahead and set the trunk native VLAN to what we would refer to as an unused VLAN. It's a VLAN that still exists in the database because it would have to exist in the database in order for us to even recognize that VLAN across the trunk. But we're not actually putting any host ports into that VLAN. So if for some reason the switch on the receiving side receives a frame that is not tagged, it will go ahead and assume that that traffic belongs to that native VLAN, which would be unused, and the traffic would be basically black holed at that point. A lot of people say, you know what, we know that VLAN 1 is the default native VLAN, and that's absolutely true. But you can actually force the tagging of that VLAN as well. So in my opinion, I would say it's probably a better choice just to ensure that you're tagging all VLANs. We try to avoid using VLAN 1 altogether because VLAN 1 by default is essentially exists. You cannot delete VLAN 1. You cannot shut down VLAN 1. You cannot even rename the name of VLAN 1. So naturally speaking, well, naturally, I should say, not naturally speaking, but naturally, that would mean that an attacker most likely would at least try to attack VLAN 1, knowing that VLAN 1 always exists, right? So, you know, the book does talk about these concepts. Make sure you prune the VLANs by using the switch port trunk allowed VLAN command. Make sure that you use or set the native VLAN on your trunk to an unused VLAN. Make sure you use switch port no negotiate on your trunk interfaces so that DTP messages are not sent. Make sure you use switch port mode access and switch port mode trunk on the interface so that you can make sure that you're statically configuring your interfaces. Switch port mode trunk does not natively disable DTP, but it does hard set the port to a trunk. Switch port mode access does disable DTP and so on. So, and then of course, make sure you set the native VLAN on the interface using the switch port trunk native VLAN command. So those would be kind of the best practiced considerations for implementing your trunk interfaces. Again, in this class, I've mentioned this a few times already. Unfortunately, we don't get the opportunity to go and see those configurations, but that would be something that you would learn in a CCNA or even a CCNP enterprise, okay? What about the VLAN trunking protocol? This is perhaps, and has been in the past, one of the most dangerous protocols that existed on a Cisco device. And unfortunately, it was a protocol that was enabled by default. They're starting to change that behavior in some of the later versions of Cisco iOS, but it was a protocol that was enabled by default on switch ports. The reason why it's so dangerous is because of the function. I kind of joked and said earlier that if it's something that auto negotiates, you should auto not use it, right? Meaning that anything that's any protocol that is dynamic by nature is inherently dangerous. Some protocols we simply can't get away from. We have to use those protocols like DHCP, like ARP in our network, and pretty much we can't just simply say, let's not use those protocols, or even routing protocols, for example. I mean, routing protocols are inherently dangerous by default because they automatically exchange information. They flood out information about the domain, albeit via multicast, but we can still see that multicast information. And by default, these protocols don't really have any security mechanisms turned on. You can certainly add security, and that's definitely something you would want to do. But inherently, these dynamic protocols are relatively dangerous. DHCP, for example, easily spoofed, easily captured because it is broadcast-based traffic. So man-in-the-middle attacks and spoofing attacks are relatively simple. So you would want to run something like DHCP snooping on your devices to protect against those types of attacks. ARP, the address resolution protocol in IPv4, also broadcast-based, very, very susceptible to spoofing attacks and man-in-the-middle attacks and poisoning attacks. So dynamic ARP inspection would be something that you would want to use for those protocols. EIGRP, OSPF, susceptible to route injection attacks by somebody just adding a rogue device, joining the OSPF domain or the EIGRP domain, becoming an EIGRP neighbor or OSPF neighbor, and injecting fake routing or false routing information into the network, either for the purposes of denial of service or for the purposes of inserting yourself into the conversation via a man-in-the-middle attack. So all of these protocols that are dynamic by nature there should always be consideration as to how you're going to secure those protocols. Traditionally, VTP was just enabled by default. As long as you had a trunk interface, VTP would be running on that interface. And it would be the simplest form of VTP, most likely VTP version 1. And there would be no security. So the issue with this, let's say I take a switch out of the box from Cisco. Both DTP and VTP are running by default, right? At least VTP would be running if it was a trunk interface. But because DTP is running, I can negotiate a trunk interface, which in turn would make VTP run. It's a really, really dangerous prospect. Now, let's talk about the purpose of VTP, and then I'll explain why it's a protocol that we need to be very aware of. The purpose of the protocol, much like DTP, VTP was designed to make our lives a little bit simpler. Simpler in the sense that it allowed us to take our VLAN database, the names of our VLANs, the VLANs that we're creating, not the host port configurations, not the trunk port configurations, but the VLAN.dat file, that VLAN database file that's stored in VRAM. And it allowed us to take that information and duplicate that information on other members of the same VTP domain. So in this particular case, we have our VTP domain called campus. They say CCDA in this example, but clearly it's not called CCDA, it's called campus. All the switches are a member of the same VTP domain. So if I go into my VTP server and I add a VLAN, I delete a VLAN, I rename a VLAN, we send out a VTP update with a higher revision number, and any switch that's part of that domain will see that update. As long as the revision number that switch receives is higher than the current revision number of its current database, it will automatically synchronize to that new revised database. Okay? So let's say that I have a VTP domain. Let's just say I don't even run VTP. I've got a switch. I've got it out of the box. I don't know anything about DTP. I don't know anything about VTP, but I do know how to configure VLANs. I know how to set up the switch and get it functioning and get it on the network. But I didn't do anything with DTP or VTP. So step number one, DTP is running on that switch. So if I plug a host into that switch, I generate some DTP messages. Most likely the port that I'm connected to is going to become a trunk, which also means that VTP can now run over that interface, the VLAN trunking protocol. Now, I haven't configured VTP on the switch. So technically, VTP is not running, but it is kind of running. It's enabled, but because we haven't joined the switch to a VTP domain, the VTP domain is null, and we haven't joined the switch to a domain, VTP messages are essentially not being sent out. But here's the issue with VTP. A switch that belongs to the null domain, meaning the domain is not set, will automatically join the first domain that it sees. So I can go back to my host now. I can open up my Yersinia application, which also allows me to generate VTP messages. And I can push out some VTP messages from my host with a domain name set, and the switch will automatically join that domain. Now, keep in mind, I haven't even logged into the switch. I haven't accessed the switch configuration. I'm not in privileged mode. I'm just a host sitting on the edge of the network, and I've now got my switch to join a VTP domain that I propagated. Now, let's assume that we had already configured VLANs on that switch. So technically, even though the switch wasn't running VTP originally, it is now running VTP, and it will now start propagating its VLAN configuration to other VTP members, which includes my host that's generating VTP messages. So now I've received a copy of the VLAN database on the host. I identify what VLANs exist, what the VLAN numbers are, potentially even what the VLAN names are. And those VLAN names might even indicate the VLAN function, server VLAN, voice VLAN, etc. Guess what? Now I can start to focus my attacks on some of those important networks. But it gets worse, because now I have a copy of the database. I know what revision number we're on. I have a copy of the database. VTP is not secured. So I go ahead and disconnect my host or whatever. I turn off VTP. I craft a new VTP message, which includes the number of VLANs and VLAN names and numbers, etc. But I make sure that that new message is part of the same domain, but with a higher revision number. And as soon as I generate that VTP message, guess what's going to happen? Whatever I have in my database, which basically is I've deleted a bunch of VLANs, as long as the VTP advertisement that I'm sending has a higher revision number than the VTP revision number on the switch will synchronize to the higher revision number, which includes deleting or removing the VLANs from the database. And a switch port that was previously configured in a VLAN, say VLAN 10, if VLAN 10 is removed from the database, that switch port basically stops functioning. It doesn't revert back to VLAN 1. It just kind of goes into no man's land, and it cannot communicate because VLAN 10 doesn't exist. There's no spanning tree instance for VLAN 10, which means there's no forwarding for VLAN 10. So in essence, long story short, with these protocols enabled by default, I've had the opportunity to now go in without ever even logging into the switch, negotiating a trunk, getting a copy of the VLAN database, deleting the VLANs from the VLAN database, and causing a major outage and denial of service on your network without ever even actually getting into the command line or the command prompt of the switch itself. This could have all been mitigated, of course, by ensuring that the port cannot become a trunk, because VTP only runs over trunks. Secondarily, it could be secured by making sure that you implement a secure version of VTP. At a minimum, set the VTP password, even though that's not generally considered very secure. But you could also run VTP version 3 with various authentication mechanisms, and you can ensure that databases can't be overwritten if you run VTP version 3 and so on. So there are ways to secure these protocols. I'm not going to suggest that these protocols should never be used, but the point is that you need to make sure that you're utilizing a protocol that, especially if it's a dynamic protocol, in the most secure method possible. It's a very, very important concept. Obviously, I've gone into a lot more detail than the Cisco text did in these topics, but I think it's a really important concept. Any protocol that's dynamic in nature, spanning tree, DHCP, ARP, an IPv6 ICMP neighbor discovery, DTP, VTP, any protocol that's going to be dynamic in nature, you should always consider what are the security elements that I can configure for this protocol to make it run as securely as possible. Not to mention the fact that even with VTP or even CDP or LLDP, these are also dynamic protocols, we can also instantiate some sort of denial of service or distributed denial of service attack on the device as well. All right. Cisco even goes as far as to say, you know what? VTP version 3 eliminates instabilities. It adds security. It adds a lot of functionality that we would need. VTP version 2 tends to be the default these days. If your network only supports VTP version 2, do not use it. All right. There are 3 modes of operation in VTP: server, client, and transparent. I would say to use transparent mode. Transparent mode, in effect, disables DTP if every switch in the enterprise is in transparent mode. If you're running VTP version 3, you can actually actually stop VTP from running. But in VTP version 2, you can't. It's either, well, it's always on. And the only way to essentially eliminate VTP is to run it in transparent mode. Transparent VTP switches do not generate VTP messages. They will accept them, but only for the purposes of passing them on down the line, right? So my suggestion to secure VTP would be to use VTP version 3, maybe use VTP initially to synchronize your domain and make sure all the switches have their appropriate configuration, and then convert all of your switches to transparent mode so that they will essentially ignore VTP messages and so on. But in VTP version 3, you could also disable the protocol. All right. Make sure that you use the security mechanisms that are built into the protocol as well. VTP version 3 offers other benefits, the ability to share not only the normal range of VLAN information, but also the extended range of VLANs. But generally speaking, if your switches don't support VTP version 3, make sure you disable synchronization for version 1 and version 2 by going into transparent mode. I would also say to go ahead and set the domain. Make sure that the domain on the switches is not null, because even a transparent mode switch will not join a domain if the domain is null. But just to be safe, if you set the domain name can only be manually changed. It will not automatically get changed if I get an advertisement that has a different domain name. So that could be a way of kind of protecting VTP as well, as to make sure that you set the domain name. Okay. All right. And that's our discussion about VTP. Now let's talk about the spanning tree protocol. Okay. Obviously, spanning tree is a relatively robust topic, particularly if you talk about all of the versions of spanning tree: 802.1d, CST, Pvst plus, 802.1w, Rpvst plus, MST, or multiple spanning tree, and so on. Each of those spanning tree protocols obviously provide a different way of facilitating the spanning tree process, but generally speaking, they all use essentially the same spanning tree algorithm. I don't know whether or not we are, well, I don't think we're going to get into the specifics of how spanning tree works in this particular class. Again, something that you would cover in maybe a switching class or CCNA. But spanning tree does operate in different modes. And there are reasons why you would choose one mode versus the other. Okay. Now, the first thing to consider is whether or not you're going to run a common spanning tree variant, or if you're going to run a per VLAN spanning tree variant. Now, Cisco devices will generally run per VLAN spanning tree variants by default. Even though it's not the best version, it is at least a per VLAN version, which gives us the ability to control the spanning tree domains on a per VLAN basis. When IEEE came out with spanning tree 802.1d, which is the D stands for don't use this version of spanning tree, but 802.1d was kind of the first implementation of the spanning tree protocol, or at least the first kind of certified and standardized version of the spanning tree protocol. But it was very, very slow to converge. Kind of the fundamental difference between rapid spanning tree and kind of classic spanning tree is how topology change notifications were propagated. In a classic spanning tree operation, whatever device detects the topology change would generate a TCN message, a topology change notification message. That TCN message would have to get propagated up to the root of the spanning tree domain. And then that root switch would have to send a TCA, a topology change acknowledgement, back to the switch that sent the original topology change notification, and then the root would start to propagate the topology change BPDUs down to the rest of the switches in the domain. Not very efficient because the root could be multiple hops away from a layer 2 perspective, and it takes a while for that information to propagate. In a rapid spanning tree, we use essentially the same algorithm, the same 4 steps: select the root, select your root ports, select your designated ports, select your non-designated ports, and we decide what ports are forwarding and what ports are blocking based on that 4-step STA process. But in rapid spanning tree, the topology change notifications are generated directly at the source. We don't send a topology change notification to the root and then get the TCA and then start sending out the TC BPDUs. We just generate the TC BPDUs directly from the source. So essentially, whenever there's a change in the topology, that change propagates directly from that source to the rest of the switches in the network. So convergence time is much, much faster. All right, so the first consideration that I was mentioning is, are we going to use a common spanning tree protocol, or are we going to use a per VLAN spanning tree protocol? In Cisco, pretty much it's always going to be per VLAN. So why use a per VLAN variation? Well, because you want to be able to influence traffic flows in your network. Basically, to provide you the ability to do some load sharing of traffic in the network, to ensure that if the distribution switch on the left, I want that to be the root for VLAN 10. The distribution switch on the right, I want that to be the root for VLAN 20. Then I'm making use of the links in between, right? So my VLAN 10 traffic would go, say, this way, right? And my VLAN 20 traffic would go to the other switch, and they would fail each other over, right? So we're making use of all of the links in our topology. We're still providing that blocking state to get rid of the loops in the topology, but we're making use of both distribution layer switches and also making use of the uplinks that go to those distribution layer switches. So 802.1d is a common spanning tree variant. Now, what does that mean? That means that every every VLAN has to assume the same root, because there's no indication of spanning tree per VLAN. Cisco modified essentially how the bridge ID format is constructed. Traditionally, the bridge ID is a combination of 2 values: the priority, which is a 16-bit field or 2-byte field, and then the MAC address, which is a 6-byte field, 48 bits. The priority is what allows us to identify who's going to become the root for that particular VLAN. Default value is 32,768. The lower the number, the more preferred. And so whoever has the lowest priority in the domain becomes the root and of that particular spanning tree topology. And if there's a tie on priority, we use the MAC address as a tiebreaker. But there wasn't anything in the Bpdu format, in the bridge ID format, to indicate what VLAN this particular bridge protocol data unit was associated to. So Cisco created kind of their own variation of 802.1d called Pvst plus, per VLAN spanning tree protocol. And in Pvst plus, they changed the behavior of they changed the format, I should say, of the BPDU to include something called an extended system ID. So they took the 16-bit priority field and they split it up into 2 parts. The higher order 4 bits, which is bit 4096, 8192, 16384, and 32768. They left those bits for the priority. So we had at least still 16 priorities that we could set. And they took the lower order 12 bits, bit number 1 all the way up to bit 2048. And they left that field for the VLAN. Just so happens that the VLAN ID field in an 802.1q tag also happens to be 12 bits. So they made it possible to identify the VLAN. That's where the per VLAN comes into play. So I had the ability to set a priority per VLAN. They didn't renumber the fields, the 16 bits, because they wanted backwards compatibility with the, excuse me, the standard bridge ID format that 802.1d used. Now, 802.1w came along. Well, I tend to call rapid spanning tree. It's rapid, obviously, but easy to remember. It's rapid. 802.1w, also a common spanning tree protocol, but much, much faster. And it, again, has to do with how we did topology change notifications, how we propagated that information. They got rid of the listening state as well. One of the transitionary states in the original spanning tree process. There are two of them, listening and learning. Both of those states were not forwarding frames, but we are kind of accepting and sending BPDUs and trying to establish the domain. So they got rid of the listening state, kept the learning state. Still the same deterministic timer, same forwarding delay timers, same Bpdu hello timer, forwarding delay timer of 15 seconds, and a Bpdu hello timer of 2 seconds, and so on. But they added some additional roles as well for the switches. They added an alternate port. They added a backup port. We don't see the backup port too often, but definitely the alternate port. So not only are we selecting a root port, which is the best way to get to the root, which would become a forwarding port, but we're also selecting a backup root port, an alternate port. So if the root port fails, we can go ahead and use that alternate port relatively quickly. The idea being that we are doing rapid spanning tree convergence. So still a common spanning tree protocol, but much, much faster. Typically with 802.1d, it might take 30 to 50 seconds to converge whenever there's a topology change in the network. Whereas in rapid spanning tree, you're talking about maybe 1 or 2 seconds, or even faster than that. So 802.1w was kind of the second variant. Cisco, of course, came up with their own second variant called Rpvst+, Rapid Per VLAN Spanning Tree Protocol. The plus, by the way, stands for all of the enhancements that Cisco added to spanning tree. All of the, what we call the spanning tree toolkit functions. Bpdu Guard, Bpdu Filter, Loop Guard, Root Guard, Ether Channel Guard, Uplink Fast, Backbone Fast. These are all techniques that are added or incorporated into spanning tree to make it even more robust. Those are the proprietary extensions that were added. That's what the plus stands for. So really, probably the best implementation, or the most common implementation of spanning tree today, is Rpvst+, Rapid Per VLAN Spanning Tree Protocol. But we will talk about MST as well. Not in this section, because in the next topic we're going to get into MST, and this is already kind of a long video. So we'll get into MST in the next section. But MST is really just a different way of implementing rapid spanning tree, because the fundamental, or the foundational version of spanning tree in MST is rapid spanning tree. So we want to make sure that we're using a standards-based protocol. Cisco's variation certainly is I guess considered standards-based now. It's not, but all Cisco devices support it. Certainly at a minimum, you want to be doing rapid spanning tree. Okay. Now what the diagram is depicting here is the idea that we talked about in one of our previous lessons. Do I run localized VLANs, or do I run end-to-end VLANs? Meaning, where does layer 2 start and where does layer 2 stop? The left diagram is kind of more of a traditional environment where the distribution layer is layer 2/layer 3. Layer 2 gets extended down to the host layer. There would actually probably be some links between those distribution layer switches as well to allow distribution to distribution communication. But the problem here is that we would have to run spanning tree all the way up to the distribution layer. The right side, we've extended layer 3 all the way down to the access layer. We would still run spanning tree on the access layer switches just as a basic protection mechanism, but not necessarily to build our overall topology, if that makes sense. You know, we would still want to always kind of have spanning tree turned on. It just doesn't become a key design element in the network. It's kind of an afterthought, if you will. All right. All versions of spanning tree use basically the same Bpdu format. Rapid spanning tree, our Vlan spanning tree has a slightly different structure to the Bpdu, but it does include all of the elements that an 802.1d Bpdu would include. So they are backwards compatible with each other. You can run a mixed environment. Some switches could run rapid, some switches can run per VLAN, but you do not get the complete benefit of the rapid convergence if you have a mixed mode environment. So basically you're gonna be kind of reverting to the standard Pvst convergence times. To take advantage of the rapid convergence, you need to run rapid on all of the switches. But you know, it's something you can migrate to as well. So for example, if you are running per VLAN spanning tree and you decide you want to go to rapid, it's a single command, spanning tree mode rapid in global configuration mode. It's not going to break your spanning tree domain. All right. Do not disable spanning tree. There are some other mechanisms that you can use, like flex links, that provide layer 2 loop avoidance at layer 2. But generally, spanning tree is a relatively benign protocol. It is a dynamic protocol by nature. So naturally, you would want to implement protection mechanisms to protect the protocol. Things like root guard, Bpdu guard, and so on. Those are the two most common protection mechanisms that we implement. But generally speaking, you would not disable spanning tree. Okay. Now, some people say, let's go ahead and disable spanning tree at the edge. But again, and that would be the reason you would consider disabling spanning tree at the edge is because somebody can, if Bpdus are being accepted, again, I can open up my Yersinia application, I can generate Bpdus, and I can change who the root is in the topology. I can maybe potentially change how traffic is flowing through the network by changing the overall layer 2 domain structure based on spanning tree. But again, if you implement protection mechanisms, maybe you implement Bpdu Guard on the host ports, on the edge ports, so that if a Bpdu is received, the port will error disable. Or you enable root guard on your uplinks to your distribution layer, assuming your distribution layer switches are the roots, so that if a superior Bpdu is received, the port will error disable because somebody's trying to claim to be the root and they should not be claiming to be the root. So I would say instead of disabling spanning tree, make sure you implement those spanning tree protection mechanisms. Okay. Now, where do I place the root of the domain? The switches have to elect the root, and the root becomes essentially the anchor point for all of the other election processes in spanning tree. There is some kind of conception that somehow traffic in the network has to flow through the root, and that's not true. The root doesn't necessarily have to be a central switch, but it can, depending on where the root is placed, it can change how traffic is flowing through the network. In this particular example, if ASW, the access switch, became the root, it is possible that these switches would then choose their route ports based on the fact that that is the essentially the best way to get to the route, and this nice big fat ether channel link between the two distribution switches would be disabled because we have to do loop avoidance. That's the whole point of spanning tree. This is, by the way, how a lot of spanning tree attacks are facilitated. Being able to direct traffic to the access layer switch when normally it would be replicated between the distribution layer switches by claiming to be the route or changing the status of that switch, or even claiming connecting a host to the interface that claims to be the route. Okay. So not only do we want to make sure that we select the appropriate switch for the broadcast domain to become the route, we would want to select the appropriate backup switch to become a secondary. In spanning tree, we do specify the primary route and we specify a secondary route. So if the primary route fails, the secondary route will take over. All right. But the key here, and I mentioned this previously, is that once the election takes place, whoever becomes the route doesn't necessarily have to process every single frame in the enterprise. All right, let me give you an example here. Let's say I have a switch here, a switch here, switch here, switch here, and somehow this guy became the route, and this link here was disabled, and that's what my topology ended up looking like. If a host over on this switch wants to talk to a host on this switch, that traffic doesn't have to go up to the route and back down to that switch. Once the process of convergence has taken place, the switches learn their forwarding and flooding techniques like they normally would. They'll learn that the MAC address is here or here, and that traffic can pass between those two devices directly without having to go through the route. So the route election in any spanning tree topology is primarily just to identify the anchor point in the network that we're basing all of the other election parameters on, right? The root of the switch, as I mentioned, is going to be based on two values. The root of the spanning tree domain, I should say, is based on two values, either priority or MAC address. Priority is a value that you can configure, obviously, whereas MAC address is burned into the switch and not something that you would configure. But the idea is that we are identifying in our environment who's going to become the route, because we want to make sure that we understand what the overall topology is going to look like. Okay? It has to be a predictable and identifiable topology. Oftentimes, you have to troubleshoot traffic flow in the network. If you don't understand what the spanning tree topology looks like, it makes it extremely difficult to be able to identify how traffic is flowing through the network. All right? If I'm not setting priorities, for example, lowest always wins in spanning tree. Lowest path cost, lowest priority, lowest MAC address, lowest port ID, whatever. In any of the election processes, the lowest is always the most important, okay? Well, naturally speaking, older switches probably have a lower MAC address number. So if you tend to place an older switch in the network and you're not manipulating the spanning tree election process by utilizing the priority, then most likely an older switch would end up becoming the route. Easy to definitely easy to configure. All right. Another consideration is if I am running layer 2 at the distribution layer and I'm running layer 2 at the access layer, most likely I'm going to be using some sort of first hop redundancy protocol to provide layer 3 redundancy for my clients. You want to make sure that that first hop redundancy protocol aligns with, sorry, that's the wrong diagram, that first hop redundancy protocol aligns with your spanning tree topology. So if DSW1 in this particular case happens to be the root for, say, VLAN 2, we would also want to make sure that it is the active router for HSRP, because what's going to end up happening is this link is going to be disabled, and if this guy is the active router for HSRP, we're essentially, instead of being able to send the traffic to the core this way, we have to send the traffic this way to get to the core, which adds a suboptimal path, or creates a suboptimal path. All right? So oftentimes when we're implementing these two protocols together, we make sure we synchronize, or at least align, the HSRP configuration with the spanning tree configuration. It goes a little bit further than that because we also have to deal with the timers. If we're running rapid spanning tree, for example, and we're running HSRP version 1, well, actually even version 2, I would think, yeah. I think both versions have the same timers. The convergence time for those protocols is significantly different, right? The hello time in HSRP is 3 seconds and the dead timer is 10 seconds. Rapid spanning tree, of course, is going to converge much faster than that. So you may decide to tune your spanning tree timers, your HSRP timers to match your spanning tree domain. All right. And definitely a consideration, because even though it may only be temporary, during a reconvergence event, you actually may lose connectivity altogether because HSRP is not converging as quickly as the spanning tree protocol. All right. Another consideration is when we're dealing with spanning tree is the metrics that are used. We don't really have to concern ourselves with this too much these days because most of the modern versions of spanning tree, including the common spanning tree variants, which came out in 2004, are pretty much default on the switches today. Traditionally, in the common spanning tree 802.1d implementation of spanning tree, we used a 16-bit value to calculate the cost, individual link path cost. This cost is utilized in the spanning tree algorithm to identify the best path to the root. The path with the overall least cost ends up becoming the best path to the root, and that in turn, that particular port that's associated to that path on that particular device would end up becoming the root port for that particular switch. Again, we don't get a chance to kind of go through the whole spanning tree algorithm process, but definitely take a look at that on our YouTube channel. We have videos that talk about spanning tree in quite a bit of detail. Okay. Obviously, in the past, when 802.1d was first created, the types of links that we had then are a lot different than the types of links that we have now, right? The types of links that we have now are much, much more robust. 10 gig links, terabit links, 10 terabit links, and so on. So if you look at the metric calculations on the left, this is actually even an updated list. It used to be even worse than this, but the top level or top speed that we reference and differentiate is a 10 gig link. And actually in the past, it used to be 1 gig was the limit. So cost, I would say, is kind of an arbitrary number. You can see here that they basically divide by 10 each time or multiply by 10 each time to include, depending on what direction you're going, to include the cost of that particular link. Obviously, a 1 meg link is going to cost you a lot more than a 10 terabit link. But this is not something you would normally have to configure. This is something that is going to be inherent in the type of spanning tree protocol that you utilize. Now, if you are running classic, 802.1d metric type calculations, or Pvst plus uses those same metric calculations. You can change that behavior and go from a 16-bit metric to a 32-bit path cost value by executing the command spanning-tree path cost method long, which would be recommended, especially if you have links that are faster than 10 gigs. In a LAN, that's probably not going to be something you're going to see, right? Maybe in the future, but for now, we're dealing with primarily 1 gig links and maybe some 10 gig links going to the data center switches and so on. All right. Another consideration is the spanning tree toolkit. There are a bunch of tools in the spanning tree toolkit. Uplink fast, backbone fast, Portfast, Bpdu Guard, Bpdu Filter, root guard, loop guard, ether channel guard, not listed here. Each one of these tools provides a different function within spanning tree. Now, I will say this, uplink fast and backbone fast, we don't really talk about that much. And the reason why is because those features are built into Rapid Spanning Tree. So if you simply enable Rapid Spanning Tree, automatically uplink fast and backbone fast are going to be enabled. Okay? So we don't have to really worry about those two. Portfast is an interesting concept. By default, all spanning tree ports go through a series of modes to try to essentially try to determine how that port is supposed to function in the spanning tree domain. If you consider a host that's being connected to a switch, in order for the switch to determine what the status of that port is, let's say the port comes up and it starts to operate. In order for a switch to determine what the status of that port is, it needs to be able to hear BPDUs, because it's the BPDUs that allow us to identify essentially what the state of the port is, what type of device is connected to that port, and are there any other downstream devices attached to that device, and so on. Problem is, hosts don't generate BPDUs. So there is a timer in spanning tree called the max age timer, which is 20 seconds, which would have to pass before we decide to move into the next mode of the overall discovery process in spanning tree. So for a minimum of 20 seconds, the port is not going to be forwarding data. Then you have these forwarding delay timers. There are two transitionary roles, or I should say states, in spanning tree to continue to kind of learn what's happening in the spanning tree topology, at least in traditional 802.1d or Pvst plus spanning tree, listening and learning. And the forwarding delay timer for those roles are 15 seconds, mandatory 15 seconds. So listening, we're listening for BPDUs, we're dropping frames, we're not processing client data, but we're listening for BPDUs, we're sending BPDUs, and we're trying to figure out what's going to happen in the topology. Learning state is basically the same thing. We're still discarding frames, but we are updating our CAM table. That's why it's called the learning state. So even though the frames are being dropped, we're updating the CAM table so that when we do end up getting to a point where we start forwarding frames, we've already kind of learned the information, and we're going to start forwarding frames efficiently instead of flooding again and then eventually going into forwarding mode. Problem with that is that both of those roles, both of those states, I should say, I keep calling them roles, they're states, both of those states are blocking states. So now we're talking about 20 seconds for the max age timer, 15 seconds for the listening timer, 15 seconds for the learning timer. You're talking about 50 seconds before anything can happen on that interface. So in essence, the port is not functioning for 50 seconds. Portfast, which is a not really considered a security component of spanning tree, but more of an efficiency element, allows us to bypass all of that. It doesn't disable spanning tree on the port, but it does say, you know what? If the port becomes active, or if the link status changes on a port, we will go ahead and put the port immediately into a forwarding state. Now, if I happen to receive a Bpdu on that port, we lose our Portfast state and we start to go through the standard blocking, listening, learning process. So we're not disabling spanning tree on a port with Portfast, but we're saying, you know what, let's go ahead and bypass all those modes and put the port into a forwarding state so that we can start processing frames for the client, because the client really technically shouldn't cause a loop in the topology. It's just a host, and it should be relatively safe to go ahead and enable that port immediately. All right. So generally speaking, Portfast, you can either enable that globally by using the spanning tree Portfast default command, or you can enable it on an interface basis by using the spanning tree Portfast command. I would say default is probably okay. It does not enable Portfast on trunk interfaces if you're running the default mode. There are some cases where you would want to run spanning tree or Portfast on a trunk if it goes to like a VMware server or something like that. But for the most part, the spanning tree Portfast default works just fine. Okay. Now, the other protection mechanisms that exist: Bpdu Guard, Bpdu Filter, Root Guard, and Loop Guard. I would say for one of these, probably not really use that much Bpdu Filter. Bpdu Filter suppresses the sending and receiving of Bpdus on an interface. And the only time that you may consider using this function is if you're connecting to another layer 2 domain, maybe a network that's not in your control, and you don't want to cross-pollinate or you don't want to cross-contaminate your spanning tree topology with Bpdus from their environment and Bpdus from your environment. So you might choose to run Bpdu Filter on the interface that goes to that particular network. Be very careful, of course, because essentially Bpdu Filter means that you're not running spanning tree on that interface. And obviously, if a loop occurs, it could be highly, well, it could definitely cause an issue. Okay. Now, Bpdu Guard is a tool that we would definitely use, and it can be implemented either statically on the interface. Most of these features can either be enabled on the interface or enabled globally. Well, with the exception of Root Guard, that's always done on the interface, and Loop Guard. But Bpdu Guard is a tool that allows us to protect against somebody sending superior Bpdus to an interface. So essentially, if Bpdu Guard is enabled on a port, if that port receives a Bpdu, the port will error disable, meaning that it will basically shut down. We can use the error disable recovery mechanism to recover the port, or we can do a no shut on the port to recover the port. But the idea is that we would enable this Bpdu Guard feature on interfaces that might be facing our hosts. Okay, we'll kind of summarize where these particular features are going to be implemented. Root Guard is probably the only other. So Portfast, Bpdu Guard, and Root Guard are probably the most common spanning tree enhancements that we can run in our environment. Root Guard allows us to protect our uplink or upstream switches, which are normally the roots, from being demoted with a downstream switch claiming to be the root. and we'll see a diagram that describes where we would implement this and why. In fact, that's what we see next here. So let's take a look at that. We should use the spanning tree mechanisms, in most cases. These spanning tree mechanisms are going to be very useful. As far as root guard goes, we would typically enable root guard on the downstream ports on the distribution switches. So basically with root guard enabled on these ports, if this switch now starts claiming to be the root, the ports will go into what we call a root inconsistent state, and they will start blocking traffic for that VLAN. They don't error disable, but it will affect the overall traffic flow for that particular VLAN. And as long as those superior BPDUs come in to the interface, the VLAN is essentially blocked. As soon as those superior BPDUs stop being received, then the ports will move from a inconsistent state to a consistent state, and they will continue to forward for that VLAN. We would typically run the Portfast and Bpdu Guard features on the edge ports. Loop Guard we would run basically anywhere that creates our backbone, essentially. The Loop Guard feature is not something that we typically use too often, but it does provide us the ability to identify maybe a loss of BPDUs or something in the network. We would use probably something like Udld for that, unidirectional link detection, but it allows us to detect the loss of BPDUs, and in the event of the loss of BPDUs, we kind of lock down the environment so that the root stays consistent. All right. So unidirectional links, that's a good segue. We just talked about that, or just brought it up anyway. Unidirectional links can cause a problem in a spanning tree environment as well. Unidirectional links is any link where traffic is only flowing in one direction. Now, we would typically see this with fiber optic connections, because fiber connections have a separate strand of fiber for transmit and a separate strand of fiber for receive. So it is possible that one of those strands gets damaged or one of those strands is not plugged in. Then you'll have unidirectional data flow. The link will still be up, the port will still be active, but we have data flow in one direction. And obviously, if I'm not receiving BPDUs, in both directions, that could definitely result in some sort of strange topology happening or some loop in the network. So Udld is not a spanning tree tool per se. It actually is a feature that we can run in lieu of spanning tree or without spanning tree, but it is often enabled with spanning tree in order to kind of add additional protection. Okay, so what happens essentially is there's a little keep alive mechanism, kind of a reflective keep alive mechanism that gets created with Udld, where a heartbeat gets sent across the link, and if we don't get a response or an acknowledgement of that heartbeat, then we can identify that traffic is only flowing in one direction, and we'll make a decision to error disable that particular port, which would then in turn kind of remove it from the overall topology. Okay. Loop Guard and Udld are kind of the same. They provide that same function. Loop Guard is specific to spanning tree, whereas Udld is kind of separate from spanning tree. But here's kind of a breakdown of the difference between them. For granularity, Loop Guard works per VLAN. Udld works per port. But it's unlikely, by the way, that you would have unidirectional flow for one VLAN, but you wouldn't have unidirectional flow for the other VLANs. So I don't know that that's necessarily a plus or a minus in either case. Protects against spanning tree failures that are caused by unidirectional links. Both of them do. All right. Protection against spanning tree failures that are caused by problems in software. UDLD is not part of spanning tree. So if for some reason BPDUs are not being sent or received based on the fact that the spanning tree process can't generate those BPDUs, but the link is actually technically not unidirectional, then UDLD is not going to perform any function. Of course, Loop Guard will, because Loop Guard is specifically looking for those BPDUs. It's not looking for just a basic heartbeat. So Loop Guard on the flip side doesn't protect against miswiring issues, but UDLD does. So for the highest level of protection, just simply implement them together. Implement Loop Guard and UDLD. There's really no reason not to. You get the benefit of both. Maybe it makes the configuration a little bit more complex, but it's relatively simple stuff. All right. As far as best practices for UDLD, we can run UDLD on fiber or we can run it on copper. I would say probably not really necessary on a copper cable. The only way that you're going to get unidirectional data flow on a copper cable is most likely if the cable's not terminated correctly. It's very easy with fiber because we have separate physical ports for transmit and receive. Maybe the transceiver on one side goes bad, or maybe the cable, half the cable is damaged or whatever. But the likelihood that your copper cable is going to get damaged to the point where the transmit path works, but the receive path doesn't work, it's highly unlikely. There's really no reason, not to consider running it. But if you enable UDLD globally, it's only going to enable it on fiber optic ports. Now you can run UDLD in kind of a normal mode or aggressive mode. We don't really get into the difference between those two, but I would say aggressive mode would probably be the best option, especially if you're using fiber optic connections. All right. All right, let's get into our next topic, which is multiple spanning tree, PoE, and EnergyWise. So the next thing we're going to talk about is multiple spanning tree. We're also going to spend some time talking about PoE and EnergyWise. Let's start by talking about multiple spanning tree. A multiple spanning tree or multi-instance spanning tree, depending on who you ask, or 802.1s, which is the IEEE kind of variation of multiple spanning tree, provides us the ability to add efficiency to a per VLAN spanning tree domain. So let's say, for example, in this particular topology, we have VLANs 21, 11, 12, and 22. Without multiple spanning tree enabled, even if we're running per VLAN, rapid per VLAN spanning tree, we are going to have 5 instances, because VLAN 1 would be included as well, 5 different instances of spanning tree running in this topology. All right. That means that we have 5 sets of BPDUs that are generated every 2 seconds on all of the interfaces, our trunk interfaces, and so on. But the reality is that even though we have 5 instances of spanning tree running, we really should only have 2 different topologies. Let's say that this is DSW1 and this is DSW2. Those would be essentially the routes for those particular VLANs. Even if I said, let's go ahead and make DSW1 the route for VLANs 12 and 11, 21 and 11, and let's make DSW2 the routes for VLANs 12 and 22, we would still have 5 instances of spanning tree. It just would happen that 3 of those instances would have one topology and the other 2 instances would have another topology. So even though we're only creating 2 topologies, we have multiple instances of spanning tree running in this environment, or multiple processes of spanning tree running in the environment. So what they did with multiple spanning tree is they said, you know what, let's create a scenario in which we don't run spanning tree per VLAN, but we run spanning tree per instance. And so rather than creating a spanning tree topology per VLAN, what we will do is we will create two instances. We'll create instance number 1 for this switch and instance number 2 for that switch. We'll associate the VLANs to the instance, and we'll run spanning tree per instance. So now we're, instead of running 5 kind of separate instances of spanning tree per VLAN, we're only running 3 instances of spanning tree. We still have the common spanning tree instance, or kind of what we call the IST in MST. And then we have our individual MSTs that we created. The initial spanning tree instance is always going to exist because we have to have some way of handling the VLANs that are not assigned specifically to other instances that we create. So there always has to be kind of that default instance that gets created. Now, you might say, well, going from 5 VLANs down, or 5 instances of spanning tree down to 3 doesn't sound like it's saving a lot in our topology, but the reality is that it is saving quite a bit because most likely we're not just running 5 VLANs in our topology, we're potentially running hundreds of VLANs, well, maybe not hundreds, but maybe 20 or 30 or 40 VLANs in our topology. And again, going from 20 or 30 or 40 VLANs down to 2 or 3 or at least instances of spanning tree, is a significant savings, right? You could actually technically have up to 4,094 instances of spanning tree. And each of those instances of spanning tree would have their own Bpdu conversions, their own bridge elections, their own pass elections, etc. So in that sense, that could be a lot of traffic that's being generated on the network. All right. So multiple spanning tree allows us to kind of create these VLAN to MST groupings. We actually map the VLANs to the MST instance, and then we run spanning tree per instance as opposed to per VLAN. So we have to create our MST region. We specify a revision number. We do our VLAN to MST instance mappings, and that's pretty much it. Then everything kind of works as it normally would. We're using, in the multiple instance spanning tree process or MST process, we're using rapid spanning tree as our underlying convergence protocol. So we're still following kind of all of the same logic, the same concepts that rapid spanning tree uses, but we are utilizing, adding efficiency by only creating spanning tree per instance. Now, that being said, there are some considerations that you have to take into account when you're running multiple spanning tree. Because the instances do not map one-to-one with the VLANs, you could have 10 or 15 or 20 different VLANs mapped to a particular instance. You have to be cognizant about some of the other protection mechanisms and some of the other control mechanisms that you implement in your enterprise to be able to support this multiple spanning tree configuration. Let's say, for example, VLAN 10 and 20 are mapped to instance 1, and our spanning tree topology is going to be based on that instance, not on VLAN 10 and 20, but I'm doing pruning on my trunk links. And I happen to prune trunk 20 from the top link, and I happen to prune VLAN 10 from the bottom link, but my multiple spanning tree instance disables the top link. All of a sudden, now I'm blocking VLAN 20, but I'm allowing VLAN 10. Well, actually, in this topology, because that port is disabled, I'm essentially blocking VLAN 10 and allowing VLAN 20 across the bottom link. So we need to make sure that, kind of the general recommendation is if you're going to run multiple spanning tree, do not do pruning on your trunk links because it's too complicated. It's too difficult to ensure that the manual pruning that you're applying to the trunk interfaces is going to match up with the MST configuration that's running in the network as well. So the general rule is just don't do it, right? It wouldn't be something that we'd want to do. The same thing applies to the second diagram there. VLAN 10 and 20 are mapped to instance 1, but in this case, because the access VLAN is assigned, the access VLAN on the top link is assigned to VLAN 10, and the access VLAN on the bottom link is assigned to VLAN 20. Again, because MST decided that the bottom link would be active and the top link would not be active, then all of a sudden our VLAN 10 traffic gets blocked again. All right. So do not run MST on access ports. Also, don't manually prune your trunk links. As I mentioned with MST, we have instances of spanning tree running. Now, it actually gets a little bit better with multiple spanning tree because even though we might have 5 or 6 or 7 instances of spanning tree, probably wouldn't. We'd probably only have 3. But even though we have multiple instances of spanning tree, we're actually only generating Bpdus. We're only generating Bpdus for the IST instance. And then all of the other MST configurations, all the other MST functionality is carried inside of that IST Bpdu. The IST instance is always active on all the ports. It doesn't matter if it's a trunk port or an access port. So use the trunk links, but don't prune VLANs from the trunks. Again, because we want to make sure that we're not filtering out VLANs that are supposed to be active. We see switch 1 and switch 2 connected here. In this particular case, they're connected with access ports that are assigned to different VLANs. MSTI 0, multiple spanning tree instance 0, is running on the bottom link, or at least active on the bottom link, and MST instance 1 is active on the top link. But again, we're carrying the Bpdus in an individual Bpdu. So MST information, we're not generating separate Bpdus for every MST instance that we're running. We're only generating Bpdus for the IST instance. It doesn't matter how many instances we actually have configured on the switch. So the individual instances do not send out their own separate Bpdus. So when we're exchanging the spanning tree information, the switches send the IST Bpdu for instance 1, and that happens to be where our mappings are created. But because it is an IST Bpdu, this Bpdu contains information for instance 0. That means that the instance, that the IST instance is active on all the ports, but it doesn't matter whether the ports are physically active or not. So switch 2 receives the Bpdus for instance 0, but it has to block one of the ports to get rid of the loop in the topology. So again, the solution in this case is to go ahead and avoid mapping VLANs to the IST instance, and then just make sure that every VLAN belongs to a custom MST instance that we create, even VLAN 1. So you might, for example, create instance number 1 and instance number 2. You would assign your active VLANs to instance 1 and instance 2. Maybe you create instance number 3 and you assign all the other VLANs that might be used in the future to instance 3 so that they're not assigned to the IST instance, that initial spanning tree instance. All right. Another consideration in an enterprise LAN environment is power over Ethernet. Now, power over Ethernet's been around for quite some time. Cisco has been doing power over Ethernet for a long time, and it's not really anything necessarily new. We understand what the concept of power over Ethernet is, right? There are a lot of different techniques for transmitting power over an Ethernet cable, but 3 of them have been kind of standardized by IEEE. And these standards are actually called Alternative A, alternative B, and 4 PPOE, the number 4 PPOE, okay? In 10 base T networks back in the old days and 100 base TX networks, only 2 of the 4 signaling pairs that we had in our cable were actually used in the Power over Ethernet standard. Alternative B separates the data and the power conductors, which kind of makes it easier to troubleshoot, and of course it separates the functionality. It also makes full use of all of the twisted pairs in the cable. The positive voltage would run, I think it was on, if I'm not mistaken, this is going way back, but I think it was on pins 4 and 5, because 1 and 2 and 3 and 6 were used for transmit and receive. So the positive would have run on pins 4 and 5, and the negative would have run on pins 7 and 8. Alternative A, that was alternative B. Alternative A would have transmitted the power on the same wires for the 10 meg and the 100 meg versions as well. And this came from the old days of doing phantom power on condenser microphones where we apply voltage to the pairs. 4 PPOE provides power using all 4 pairs of the twisted cable. And we can, was primarily implemented to add additional power channels for things like high performance wireless access points or charging functionality, or maybe PTZ cameras and so on. We do see different variations of power. The original standard 802.3 AF, which is a 2003 standard, provided power for up to 15.4 watts of DC power. That would be about 45 volts DC, maybe 44 volts DC, but a very low amperage, right? About 350 milliamps on each port. And in that particular case, it was somewhat limited because only about 12.5 to maybe close to 13 watts would be available to power a device in that particular case. Then they came up with an updated version in 2009 called 802.3 AT. And this is what a lot of people will simply refer to as PoE plus, or with the plus symbol. And that provides up to about 25.5 watts of power for type 2 devices. But in this particular standard, we prohibited devices from actually using all 4 pairs for power. And not that that's really important, but, you know, it's just a side note there. They actually have a new standard that that's not listed on this chart here, which came out in 2018, called 802.3 BT. And this is the 4 PPP, I keep saying PPP, 4 PPPoE, I did it again, or what we call PoE++. So we had 2 different power types, up to 51 watts for type 3 devices, and up to 71, I think about 71.5 watts, if I'm not mistaken, for type 4 devices. But each pair in the twisted pair would actually have to handle a current of about 600 milliamps, or up to 960 milliamps. 600 milliamps would be for about the type 3 devices, and up to about 950 or 960 milliamps for type 4 devices. And then we also had support for running this over 2.5 G base T, 5 G base T, up to 10 G base T, and so on. There's other variations. There's single pair power over data lines. But we understand what the use is for power over Ethernet, right? Power up a phone, power up an IP camera, maybe an antenna, or a microwave link, a Cisco, a microwave link, a Cisco phone, decoders. I mean, really just anything that would be able to accept this DC power based on the wattage that's being provided. The power sourcing equipment, which is the switch itself, these are the devices that are actually providing the power over the Ethernet cable. Most likely it would be a switch, but it could be an injector, right? You might have an external PoE injector. This would be referred to as a mid-span device. Maybe you have a non-PoE capable switch, but you have a PoE device that you need to attach to the network. So you would use a PoE injector to inject power. The power device is the device that's actually accepting the power on the other end. A lot of times these power devices will have auxiliary power options as well, to connect an external power supply if you need an external power supply. The idea of PoE is kind of uniform now. Most devices now support PoE, basically the standards-based power over Ethernet. The way that it works is, as far as defining how we're going to provide power, is the power is supplied as what we call a common mode signal over the different pairs that are in the Ethernet cable. So we can inject power into the cable with mid-span power or the power device itself without affecting the overall transmission of the data that's being passed over the wire itself. So we have essentially 4 types of devices, just to summarize. A PoE type 1 device would require about 15 watts of power. A type 2 device would require about 30 watts of power. A type 3 device would require about 60 watts of power. And a type 4 device would require, or at least could get, up to 100 watts of power, depending on the devices. All right. Now, I don't know that we need to really get into the detection mechanisms. There's a passive detection mechanism that's built into these devices. It is a resistor that's put into the circuit path to reduce the voltage amount, anywhere from like 19 to about 26 kilo ohms, to reduce the overall voltage, and we can detect whether or not a device is attached. And then we can specify or provide the power that's necessary for those particular devices. Now, there are actually 8 classes of devices. We don't really see those 8 classes of devices in most modern networks today, and we don't really need to get into the discussion of each of the classes. But oftentimes these devices will negotiate the power that they need by using some sort of data link layer discovery protocol. In Cisco, that discovery protocol is CDP. The Cisco discovery protocol, we use various type length value formats in that CDP protocol to define or to negotiate and signal the power that's either available or the power that's necessary. In open standard networks, we would have a similar protocol, LLDP, that would provide that functionality. So, power over Ethernet, something that we see all the time these days. And like I said, most switches are going to be supporting anywhere from 15.5 watts up to 30 watts of power, depending on the type of device. Now, if you think about this, in the past, this was not a major concern in most enterprises. It was kind of like a feature that was added that provided us, a bit, additional, functionality. We didn't have to plug in our devices. This primarily came from the need to power IP phones because a traditional PBX, the phones were powered over the line that was connecting the phone to the PBX. And we could provide some sort of redundant power at the PBX so that if the power in the building goes out, the phone system is still powered and the phones would still function because they're receiving power from the central location. So we wanted to kind of emulate that or duplicate that in a standard Ethernet environment. We didn't want to have to plug the phones into the wall or have separate power sources for each of the phones with battery backup and so on if the power in the building goes out. So power over Ethernet was kind of created for this IP telephony environment. We'll talk a little bit more about how the phones manage that process in a minute here. But, you think about it, as the devices started to get, as power over Ethernet became kind of more of a standard, more and more devices were designed to utilize that feature. And now all of our access points in the network, all of our IP cameras in the network, maybe some secondary networking devices, small computing devices, certainly IP phones and so on, are all taking advantage of this power. So the switches themselves have to now support possibly up to 700 to 1500 to a couple of thousand watts in the chassis itself to be able to support all of the ports on the line card drawing power from the switch. And that takes energy, right? That takes resources. It takes electricity. So the more power that a switch is providing to the endpoints, the more power that switch is going to draw from the power that it's receiving from the utility. And that's where EnergyWise comes into play. We'll talk about that in a little bit. To support power on IP phones, particularly Cisco IP phones, utilize negotiation techniques to identify how much power the phone is going to require. Initially, it will get a basic level of power that will allow the phone to function initially, and then it might negotiate additional power for some of the enhanced features that the phone might have to run. We use CDP to process that. Then the phone goes through and it gets its DHCP. By the way, CDP is also used to identify what VLAN the phone belongs to, the voice VLAN ID or VVID. And then we run our DHCP, we get our IP address, we get in that DHCP lease, we get a TFTP address assignment. The phone will then go to a TFTP server. It will download its configuration from the TFTP server. Of course, based on this particular discussion, the phones are getting their power through the Ethernet cable. And some phones, particularly some of the more advanced phones, require a minimal set of power or a minimal amount of power to power up and do their basic bootstrap functions and start loading. And then they will require additional power to power on the display and provide the other functions that the phone is going to provide. So the phone allows, because we're getting power over the Ethernet cable, because we're separating the traffic from the PC, the phone itself is a switch as well. So the PC will plug into the phone and the phone will plug into your infrastructure switch. We have a single cable that facilitates all of this communication. Okay. The phones themselves don't require wall power. They can actually be plugged into the wall. Some people might choose to do that, but in the most cases, we'll just get power from the PoE compliant switch that we're plugged into. If for some reason you're running a Cisco phone and you're running a non-Cisco switch, you would probably have to utilize LLDP in order to facilitate that negotiation of the VLAN and the power, but that's fine. The Cisco phones support LLDP with no problem. All right. And most Cisco phones, not all of them, but most of them support or have an integrated switch as well. So they can support connectivity to upstream or and downstream devices and even manage that connection as well. Okay. So let's walk through a quick case study here. We're just going to kind of go through this. In this task, we're going to determine how PoE will be factored into the design and the implementation of a wireless network. We'll determine how PoE will be factored. Well, that's a duplicate. Never mind. There are 36 IP phones requiring 4 watts each, which provides a total of 144 watts. We have 20 IP phones that require 7 watts each, making a total of 140 watts. There are 2 1700 Cisco access points that require 15.4 watts each. That's a total of 30.8 watts. 2700 series access points, 2 of those, 16 watts each, which is 32. The switch on the floor has a PoE output of 740 watts, and this is more than the total requirement of 172 watts. The switch on the floor has a PoE output of 370 watts, and this is more than a total requirement of 174.8 watts. Not sure what they're trying to differentiate there. I guess we have essentially, let's see, 100, 200, 284 plus 30 is 320.8, 360. So I guess they're kind of splitting it up. I was trying to add up all the power, and it looks like A and B are kind of split between 2 switches, and C and D are kind of split between 2 switches. Because if you add up the total, it is over 300 and something watts, and that's what they're kind of saying here. 172 watts for one switch and 174.8 watts for the other switch. Didn't really describe that very well, but that's okay. So the information about how the power of an individual device needs are what the needs are for some devices, given a maximum consumption. Other devices, it's based on a PoE class. So for building A, we should calculate how much power IP phones and access points needs to and determine the power budget for the switches. Now, they're doing this manually. Fortunately, Cisco has a tool called the Power Calculator tool on their website. If you go to cisco.com and you search for Power Calculator tool, you will see the tool, and you can put in the switch type, you can put in the ports, the modules, everything that you're going to be connecting, and it will create this budget, this power budget for you. But in this case, we're kind of doing it manually. So for building A, we need to create this power budget. For the 5th floor of the building A, we calculate the budget of the stack of switches because they are in a power stack, meaning that they're individual stackable switches that have cross-connected power cables so they can share power, pool their power resources. If a power supply fails, another power supply can take over, and so on. The power stack technology has been around for quite some time, but it allows us to kind of share power. The PoE budget for all the power devices in the building is sufficient. First floor, 36 times 4, so 144 watts for the phones, 30.8 watts for the access points, a total of 174.8 watts, but we're running a 2960X48 LPD-L, which delivers 370 watts of power. I'm not going to read all of these, but you get the idea. Based on the switch model, based on the available power on that switch module, is it going to be enough? I would say with the stackable switches, it's relatively simple to do the power calculations. It's when you get into the chassis-based switches where you can have redundant power supplies, you have line cards that require power, you have route processors that require power, fan trays that require power, and then also your PoE requirements. It gets a little bit more complicated. Okay. All right, so it does say here that not all the switches in Building B can provide PoE to the devices. Since buying a replacement PoE switch is not an option, we will have to do either mid-spans or just power devices individually by plugging them into the wall. All right, I would say a mid-span PoE might be better, but keep in mind with mid-span PoE, you're still plugging in that mid-span injector. I mean, it has to get power from somewhere to be able, so it usually has an AC connector to the wall, and then it's injecting power into the line, DC power into the line based on that. Okay. All right. Another that kind of concludes rather abruptly our discussion about PoE. Another consideration is data over subscription. As we add more and more devices to the enterprise, whether it be wireless devices, of course, the advancements of wireless have increased the bandwidth consumption of wireless quite significantly. In the past, wireless maybe provided 54 megs of throughput or maybe 11 megs of throughput with some of the legacy concepts, but now we're talking about gigabits of throughput or gigabytes of throughput. So we have to take that into consideration. Devices, endpoint devices are consuming more and more bandwidth. We might have been able to connect devices in the past using 10 meg connections, but now everything is pretty much standardized on gig connections. So you have to consider oversubscription, meaning that based on the number of devices that are attached at the access layer, you could easily consume all of the bandwidth on your uplinks going to the distribution layer or even to the core layer. Now you can implement quality of service mechanisms to handle congestion during busy times, but QoS mechanisms are not going to, they will allow you to prioritize traffic and ensure that the important traffic maybe is not affected by the loss of bandwidth, but it's not going to get you bandwidth back. You're still going to have queuing mechanisms that ultimately will probably have to do some sort of tail drop on less important data flows to ensure that the more important data flows are still being processed. Increasing the bandwidth by aggregating links together or even, just increasing the type of or changing the type of connection we have from, say, 1 gig to 10 gig or a terabyte or whatever is probably your best solution. You may still decide to run QoS because there may be instances of congestion that you run into, and you still want to be able to manage what gets dropped and what doesn't get dropped, based on your priorities. But QoS is never a mechanism that's used to increase bandwidth. It's a mechanism that's used to manage bandwidth. So upgrading the links between, say, your distribution and core switches to 10 gig links is maybe better than adding additional gig links to an ether channel or something like that. But there's a cost to that as well, right? Talked about layer 8 and 9 of the OSI model, budget and politics. Well, budget is definitely one of those things to consider. Okay. Another concept is that we talk about is wake on Lan and EnergyWise. A lot of times devices, in order to save power, in order to essentially ensure that the device is kind of goes into what we call a sleep mode, if you will. It will power down, or at least semi-power down, until it sees these magic packets, which the device is designed to respond to power the device on or to bring the device up. All right, so the WOL feature, a Wake on Lan feature, allows you to remotely power on devices or sleeping machines so that you can access those devices for management, you can update the software on those devices, and so on. So basically the principle is the device shuts down, the NIC is still receiving power, from the AC power from the PC. So it keeps listening on the network for those magic packets. Once the magic packets arrive, then the device does whatever it's programmed to do based on the receipt of those magic packets. It doesn't have an IP address. It's not going to respond to data requests. It's not going to respond to ARP requests and so on, but it will respond to those magic packets. If there is a layer 2 switch between, say, a router and a PC, which is obviously going to be the case in a lot of designs. The switch does not know which port the PC is connected to on the other side. It doesn't have any visibility of the layer 2 domain on the other side. But routers do not forward broadcasts. They create them, but they do not forward them. So in that particular case, we may lose some functionality depending on where the messages are coming from. So in this particular network setup, PC 1, 2, and 3 are the client PCs that need to be woken up. PC 4 is the Wake on LAN server and the DHCP server. PC 4 has an address of 172.16.3.2. It's not documented on the diagram here, but it's in the book. The client PCs are configured to get an IP address from the DHCP server. And there are 3 scopes for each of the VLANs. Notice that each of the PCs are in different VLANs. So we're running a multi-layer switch in the middle, which is basically a router with SVIs and routing on that switch. Switch 1 and switch 2 are 2950s. They're used as layer 2 switches, and then the 3750 in the middle is used as our layer 3 routing device. PC 1 and PC 4 are connected with the same VLAN. PC 2 and 3 are connected in VLAN 2 and VLAN 4. Okay, so that being said, there's a couple of things that we have to take into account, right? For VLAN 3, well, that's actually kind of interesting. I don't know that that would actually be possible. I suppose it would. Actually, it would, yeah, because the link between switch 1 and switch 3, or the middle switch, is a trunk link. It's not a layer 3 interface. I was thinking there's no way that they could have VLAN 3 on one side of the router and VLAN 3 on the other side of the router. But in this case, we're using a multi-layer switch. So there's a layer 2 function, and then there's a layer, kind of an internal layer 3 function on the switch. So for VLAN 3, we don't have really a lot of issues because VLAN 3 spans to the DHCP server. But the issue that we have with VLAN 4 and VLAN 2 is that those are in separate broadcast domains. So any protocol that relies on broadcasting will not, across, from the Wake on LAN server or DHCP process on PC 4, will not function correctly because routers or routing processes never forward broadcasts. So we would have to consider what the effect would be on our WOL magic packets, being that those are flooded or broadcasted. Certainly with DHCP because it's broadcast based. Now DHCP is a little bit easier to deal with because we have IP helper address that we can use to essentially proxy those DHCP requests. But definitely something to consider. We would probably lose the Wake on LAN functionality in that particular case, but we can definitely facilitate the DHCP process. All right. The last thing we'll talk about in this particular section here is EnergyWise. Cisco EnergyWise is just like any other EnergyWise technology. It's a green IT technology. Basically what happens is you create this EnergyWise domain. It's treated as one unit of power management, almost like a network management community, like a VLAN, a VTP domain, if you will. So you can have different devices in this EnergyWise domain, switches, other network devices, IP phones, endpoints, and so on. The domain members actually will forward messages to other members and to the endpoints in that domain. And the domain members themselves can get power from various sources. They can get power from AC, they can get power from PoE, and so on. But a EnergyWise domain member can only belong to one domain. Now, the idea here is that we are creating this EnergyWise domain to be able to manage how much power is necessary to facilitate the function of the devices. Cisco recommends that you don't have more than, say, 50 devices that are metered or sub-metered in an EnergyWise domain. We can actually name the EnergyWise domain. We can specify the protocols and the port numbers that we're going to use for EnergyWise functionality. We can even create authentication for it as well. There are different phases of EnergyWise, phase 1 and phase 2. It's a little bit beyond the scope of this class to get into the specifics of the implementation of EnergyWise. Here, they're just kind of basically mentioning it. But the idea is that, you know, a Cisco phone, let's take a phone as an example, because that's kind of the most common type of endpoint that can take advantage of this functionality. A Cisco phone needs a certain amount of power. You take like a 9970 phone that has a nice big display, it's got a video camera, it's running Android OS, and it's got all this functionality built into it, touchscreen display and all that. When the phone is being utilized and basically fully functional, it's going to have a certain amount of power that it requires. And that power draw is going to be pretty significant, you know. But if the phone is idle, the display can turn off, some of the functions can be disabled and so on temporarily, and it's going to require less power in that particular environment. So EnergyWise allows us to query and summarize information from these devices to identify how much power they need based on the current state of that particular device. The idea being that we're able to essentially limit the amount of power that's being utilized by our devices. I mean, at night, you know, when everybody goes home, is it really required for every single IP phone to draw the maximum amount of power and have its display activated and so on? So this is actually something that didn't really exist not too long ago. Obviously, with green technology and green IT, it's something that was created. So there's a little bit more to it, obviously, than the just, you know, kind of talking about what it does. But that's beyond the scope of what we're trying to achieve here. All right. The next topic, we have two more topics, actually, three actually, that we're going to be discussing. But the next topic is port aggregation. Okay. Port aggregation is a feature that allows us to take multiple, what would be normally independent connections, and logically join those connections together for redundancy purposes, but also for additional throughput purposes. The little circle around the lines tends to represent one of these bundled channels. We call these ether channels. At least Cisco calls them ether channels. Some vendors call them aggregation channels, like a link aggregation group or a lag. Some of them call are called ether channel. Some of them are called bonded links. There's other terms that other vendors use. But the bottom line is that we're joining these channels together so they look like one logical circuit. Okay, they're four separate physical circuits, but they look like one logical circuit. The benefit of this is, of course, we do get the redundancy. We would have the redundancy anyway if we had 4 active links that were individual, but some of those links would have to be disabled because of spanning tree, because we have to prevent the loops in our topology. But by bonding the links together, from spanning tree's perspective, they look like a single aggregate link, and all the physical links can be active because they've joined this logical port channel interface or port channel group. You can create these ether channels at layer 3. You can create them at layer 2. And then, of course, based on whether it's layer 2 or layer 3 will determine what type of configurations you can put on the port channel interface, whether it's an IP address and some sort of routing on a layer 3 ether channel or trunk configurations on a layer 2 ether channel. All right. There are actually 3 ways that we can create these ether channels. We can use LACP, LACP is an IEEE standard for Ether channel, the Link Aggregation Control Protocol, or specifically 802.3 AD. Or we have PAGP, the Port Aggregation Protocol, which is a Cisco proprietary implementation of Ether channel. Or we have a no protocol channel, which is what we call a static persistent channel, where we just simply specify that the mode is going to be on both sides, and we assume that the Ether channel is just going to be active. So LACP has two modes of operation, active and passive, very much like DTP had auto and desirable. We see that here, desirable and auto. Passive means I don't send out negotiation packets to form the Ether channel, but I will accept them, and I will, if I'm instructed to, I will become an Ether channel, whereas actively sends out messages to become an Ether channel or to form the Ether channel. In the case of PAGP or PAGP, desirable sends the messages and auto listens for the messages. So if I have auto to auto, the Ether channel is not going to form because both sides are passive. If I have passive to passive, the Ether channel is not going to form because both sides are passive. These Ether channel mechanisms are not compatible with each other. Whether you choose to use one or the other is entirely up to you. I'm assuming there are some differences, obviously, between them, but ultimately, the goal of Ether channel is to form the Ether channel bond, right? To form that Ether channel link. And both of them are effective in doing so. Obviously, PAGP being Cisco proprietary, you'd only run it on Cisco devices. So Lacp or LACP is kind of what most people will use today. And they'll most likely configure both sides of the channel as, let me do that again. They'll configure both sides of the channel as active, just to ensure that the Ether channel is going to form. Some people like to use static persistence on Cisco devices. We'll just assume that the Ether channel is functioning, and we'll force the ports to join the Ether channel group, because sometimes the negotiation of an Ether channel link doesn't work. We actually see that quite a bit. Whether you decide to use static persistence or LACP or PAGP doesn't really matter. Obviously, we understand the basic differences between them. But what is important is that is how you decide to place ports into the Ether channel. Because we are joining multiple interfaces together, there is an algorithm that has to be chosen, or an algorithm that has to be used to decide how we're going to load balance over those port channel interfaces, or those Ether channel interfaces, I should say. And the way that we do that is we do it based on what we call an Ether channel load balancing option. And there are several different Ether channel load balancing options. It depends on the switch model, but we could do it based on destination IP. So if destination IP is A, we'll send it over this link. If it's B, we'll send it over this link. If it's C, we'll send it over this link. We could do it based on destination MAC. We could do it based on a combination of source and destination IP or MAC, source IP, source MAC, port numbers, destination port numbers, and so on. But this hashing algorithm is used to create a binary calculation, or at least a binary output, that allows us to identify which port the channel is going to go over. So the way that this basically works, this is not exactly how it works, but we'll just kind of describe it this way. This is how a lot of Cisco books will describe it, is let's say that I have a two-port Ether channel. All right. What I have to do is I have to assign an interface index to each port. Well, if I have two ports, 2 to the power of 1 is equal to 2. I'm using binary to index these ports, which means I need 1 bit in my calculation, in my hash, to be able to identify two different ports. So maybe interface gig 00 is index 1 or 0, and interface gig 01 is index number 1. Okay, so now let's say that I'm doing source destination IP load balancing, and the source IP is 10.10.10.10, and the destination IP is 10.10.10.11. Well, actually, I guess we could do that, 10.10.10.11. All right, we're going to use Boolean math to be able to calculate which interface index this particular traffic is going to pass over. And that Boolean operation is what we call an XOR operation. So XOR operation comes from the old transistor days where we had two inputs and one output, and we would basically apply voltages to those inputs to result in some sort of voltage output. And that's pretty much how computers work today. But the XOR operation is as follows. If I have based on the inputs or whatever, if I have a 0 and a 0, that's going to result in a 0 on the output. So 0, 0 equals a 0. A 0 or a 1 will equal a 1. And a 1 or a 0 will equal a 0. And finally, a 1 or a 1 and a 1 will equal a 0. Different than the OR operation. This is an exclusive OR operation. So exclusively, one bit has to be different from the other in order for the output to be a 1. Okay? So now what I do is I basically take my IP addresses and I take the last bit of each of the IP addresses. So 10 is 1010 and 11 is 1011. I take this last bit. Well, let me just hit a return here. I take this last bit and I perform that exclusive OR operation. And the result of that exclusive OR operation is a 1, which means that traffic is going to go over that interface. If the result of the exclusive OR operation is a 0, the traffic would go over that interface. So you look at this table below and you say, okay, what do these numbers mean, right? If I have 2 ports in an ether channel, I have 4-to-4 load balancing, right? If I have 3 ports in an ether channel, I have 3-to-3-to-2 load balancing. If I have 4 ports in a channel, I have 2-to-2-to-2 load balancing, and so on. So what is it that they're trying to tell us? Well, basically what they're saying in this particular case is that we're identifying the polarization that occurs on the links based on these exclusive OR operations. Let's say that I add a 3rd port to my ether channel. Not recommended, but I add a 3rd port. How do I index that port? I can't index with a single bit anymore because I don't have any more bits to index with. So now I need 2 bits to index with, which is going to result in 4 indices being created. 4 indexes being created. A 0, 0, a 0, 1, a 1, and a 1, 0. But we also have the 1, 1. And we can't just simply ignore the 1, 1 because some of the Boolean operations are going to result in an interface index calculation or a hash of 1, 1. So we have to assign 1, 1 to at least one of those 3 interfaces. And this is where polarization occurs. Now all of a sudden, gig 02 is getting, has 2 indexes assigned. So theoretically, I suppose that could mean that gig 02 would receive twice as much traffic. It just depends on how the calculations work out, but certainly it's going to receive more traffic than the other indexes or the other interfaces that only have 1 index assigned. So that's where we see this kind of 3-to-3-to-2 ratio. And so that's why also when you're creating ether channels, you typically would want to create them in binary pairs, right? either 2 or 4 or 8 or 16. Now, that doesn't guarantee that you're going to get true load balancing. It really depends on the ether channel load balancing algorithm that you've decided to use. And it depends on the type of traffic that's being generated. Polarization is an effect where basically one interface receives more traffic than the other interfaces. If, for example, you have two clients that are always talking to each other, that traffic is always going to go over one interface because the Boolean operation is always going to result in the same calculation. So you may decide to change the algorithm that you're using for the load balancing mechanism. There's no way to get it to do true load balancing like a per frame or per packet load balancing, but you can kind of try and get it to match up as best as possible. All right. Now, this is a really simplified way of considering how this actually works. It's a little bit more complicated, but it's good enough for what we're trying to do today. All right. I just wanted you to understand what they meant by these numbers here. All right. What about a virtual switch system or virtual switch stack? I like to call it a virtual switch stack, but it is technically virtual switch system. It allows us to cluster devices together. Only two devices. This is not a physical switch stack where we're using like StackWise technology, but we can cluster two devices together to create what we call a virtual switch domain. And then we can implement multi-chassis ether channel or MEC to essentially create this ether channel link across multiple switches. So physically, it looks what it looks like on the left. Logically, it looks like what it looks like on the right. So we do have this option. We can also do ether channel across physical switches in a switch stack. It doesn't require the use of the virtual switching system, but it does allow us to provide the ability to create ether channels across those devices as well. So that's what the virtual switch domain would look like. We can have, again, as many interfaces as we want to be able to communicate between those switches. But with the VSS, one chassis is always going to be designed or defined as the active virtual switch, and the other is the standby virtual switch. The active virtual switch is the one that's running the supervisor engine. It manages all the control plane functions, which are the higher level routing functions and whatnot. And then the data plane is active on both of the switches. All right. The bond between the two chassis allows us to create this logical interface or logical switch, I should say. There's obviously signaling and control information that we're going to exchange between the two chassis to allow the exchange of reachability information, and that data is transferred over something called a VSL, a virtual switch link, and that is typically going to be formed over the ether channel interface, and that ether channel interface can be anywhere from one port, which would not be ether channel at all the way up to 8 physical ports. And I think it even goes higher now, depending on the switch model. All right. We need to make sure, of course, we have redundancy for our VSL. If the virtual switch link fails, then both switches, we kind of get island routing, if you will, or island control plane functions. The standby supervisor assumes that the other switch has been lost. It takes over the active role. So now we have really two active supervisors, and we don't want to see that. All right. Again, not really getting into the configuration of this technology, but taking a look at it. All right. StackWise, another feature that's available with Cisco switches. Now, this is a physical switch stack, as opposed to a logical switch stack, but StackWise technology has been around for quite some time, and it provides us the ability to stack both the data plane functions of the switch as well as the power functions. Basically allows us to link multiple switches together to establish a single switching unit. And so on these cables on the left here, this is looks to be like a 3750 stack. No, it's not a 3850. I think it is a 3750 stack. But these cables here are proprietary physical layer connections that provide this ring of connectivity. So it goes from here to here to here to here to here and then back to here. So we have this ring of connectivity and provides, gosh, anywhere from 100 and I think it's 170 gigs up to close to 500 gigs. It probably even goes higher than that now with some of the kind of more advanced switches. I think if I remember, for the 3750s, it was 170 gigs. I'm not sure what the stacking bandwidth is for some of the, like the 9000 series switches and so on. But I know it's a pretty high number. In the past, if we wanted to interconnect our devices, we would have to use the link on the front of the switch, the links on the front of the switch to create really a switched port that would allow us to communicate between the switches. And that would be limited, the bandwidth would be limited to however many ports we had connected that may or may not be bonded together. But with this particular backplane, it's different than that scenario, because with this backplane, what we're doing is we're taking what would normally be separate physical devices, and we're creating one virtual device with one command line interface, one configuration, and as opposed to separate command line interfaces and separate configurations. If a switch were to fail, we would lose half the bandwidth of our ring, but we would still have connectivity. If two switches failed, then the ring would be broken, but hopefully that doesn't happen. Here you're seeing the power stack as well. So with redundant power supplies, in a 3750 stack, you can have up to 9 switches in the stack, but only 4 of those switches can be linked together with power. So typically we would just maybe link 3 of them together, do like a 3-3-3 type of scenario. But the stack-wise functionality is very, very powerful because it provides us the ability to stack these switches together. Like I said, the 3750, not quite as fast. I know that the 3850 does about 500 gigs. I think it's about 480 gigs of throughput. But it's not that stacking hasn't been around for a while. It has been around for a while. But in fact, I remember when I went to JPL, that's where I kind of got started in IT. We had 3COM switches. Actually, they were 3COM concentrators. So they were actually 3COM hubs, but they had managed IP addresses. So they were managed hubs, and they stacked together to create a virtual stack. They weren't very efficient because they were hubs, but that gives you an idea of how long this kind of technology has been around. Pretty much most of Cisco's enterprise class switches have some sort of stacking capability. It comes in different formats and whatnot, but it does provide stacking capabilities. So when you do create a switch stack with the stack-wise interconnect cables, you're creating this virtual switch. So as far as Ether channel, we don't have to use a multi-chassis Ether channel, even though it is technically multi-chassis Ether channel, because the switch looks like a single switch on the stack-wise side. So when I'm creating my Ether channels, I would separate the members, the port members of that Ether channel across different switches in my switch stack. And obviously, if one switch fails, one physical switch fails, we would still have connectivity. All right. And again, because we're bonding these links together, spanning tree would not be a big concern for the individual links in the Ether channel bundle. All right.